Welcome back. Today's topic is displacement current. In the last video lecture, we have discussed about self and mutual inductances, and we have also seen how to calculate effective inductances when inductors are placed in series and parallel, and also for aiding and opposing couplings. In this video lecture, we will see how to determine the displacement current. Now, so our target will be to develop an expression for displacement current and employ that one to determine the displacement current. First of all, what do you mean by displacement current? You might have heard about this conduction current, which is nothing but movement of electrons, right, in any conducting material. Displacement current is one such quantity which generally appears in Maxwell's equations. It is defined as the rate of change of the electric displacement field, what we call it as ID, which is the common representation of displacement current. It is defined as so it is generally observed in a capacitor. It is the rate of change of your electric displacement field. Now, we know that when a capacitor is connected across a source, when it starts charging, you know that it slowly starts charging. There is no conduction of charge between the plates, literally speaking. However, because of the when a conductor starts charging, there is no conduction of charge between the plates. However, because of the change in charge accumulation on the plates, on either of these plates, there will be a displacement current which will be happening. And the current, due to the changing electric field, because the charges are being accumulated on either of these plates. If the charges are accumulating from one, they're moving from one plate to another plate, which means that there's a change in electric field, right? And the current due to this changing electric field, it is termed as a displacement current. Now, displacement current is normally represented by IT, whereas the displacement current density is represented by JD. Normally, what we do is nothing but rather than this ID, we'll take JD. Let us suppose capital D represents electric flux density. Then the displacement current density is normally given by this particular equation. JD is equal to rho by dou T of D, capital D, where capital D represents electric flux density vector. So, if you do have JD, which is nothing but dou D by dou T. Now, if you want ID, which is nothing but right over the surface, then we need to go with the surface integral of current density. Then this JD is nothing but this one, the same I am writing here. This is your equation for determining the current density. Now we will try to apply this particular equation for determining the current, displacement currents. And you also know that ID is nothing but line integral of H dot dl, right? Now if you can apply this Stokes theorem for this one, this closed integral will become open integral, length will become surface. This is del cross H, right? Del cross H dot ds is equal to same ID, which is nothing but here. So if I remove the surface integral on either sides, then what is my expression? Del cross H is equal to JD. This is one of the expression which we generally employ. Del cross H is equal to JD. What is JD? You have seen already JD. It is dou D by dou T, right? This is a relation between magnetic field intensity and electric flux density vector. Okay, so we will try to employ these equations in the tutorials, which we do have at the end of this week. So now let's determine a simple. Let us determine the displacement current with a simple example. Now, see, there is a parallel plate capacitor with a plate area of 5 square centimeters, which means A is equal to 5 square centimeters, which is 5 10 to the power of 4 meters. Plate separation, which is nothing but D, 3 millimeters, which is 3 10 to the power of 3 meters. This is voltage V, thousands T, 10 cube is 1000, right? And calculate the displacement current, assuming this is epsilon. So what they are asking, displacement current they are asking. How to determine the displacement current? Displacement current, it is JD dot S. Right, JD dot DS. No, I don't have anything to integrate because it is a parallel plate capacitor with fixed dimension. So I can directly take it as JD into S. No need of integration. Integration will be done if the area is non-uniform. Here it is very uniform. They are saying that it is having a plate area. Parallel plate capacitor. So fixed size. And we know that area. It is 5 square centimeter. So I'll directly take it as JD into S. What is JD? It is dou D by dou T. What is D? You know, again. D is nothing but epsilon naught E. And what is E? You know, it is V by D. So everything you know here. So just I am rewriting the equations. Now, if you carefully see, ID is equal to JD into S. JD is nothing but dou D by dou T into S. D is nothing but epsilon E by S. E is nothing but V by D, right? So I'll write it as 1 by D dou V by dou T into S. This is my ID. So what I'll be getting, ID is equal to epsilon naught is he has already given us 2 epsilon naught. 1 by D I do have, it is 3 into 10 to the power of minus 3. Dou V by dou T. V is already given for me. I should differentiate it with respect to time. 50 sine will become minus cos, sorry, sine will become cos, right? 50 cos 1000 will become again here. So it is 50,000 cos 1000 T into surface area. I have already known 5 into 10 to the power of minus 4. This is my answer. Okay. Yeah, you can find the. This is JD. You can calculate. So I have directly done this one, right? So you can directly calculate that one. This is your equation. Or you can go through step by step. You do have V. When you do V by D, you will get E. Again, epsilon E will give D. When you do have D, dou D by dou T, you will get JD. When you do have JD, JD into S will become ID. So you can go stepwise, or you can directly do this entire equation in a simple problem, in a simple way. Done. So I hope that now you are able to determine the displacement current and try to solve this particular problem in the class. Okay, thank you.